I believe we can start, and so let me introduce myself, of course, first of all. So my name is Denis Sidorov, and I represent Institute of Energy System of Russian Academy of Science, and also I represent IEEE PS Russia and the Siberia chapter. So I am chapter chair since 2017 until now. So, and today we have the great speaker, Professor Sayfur Rahman. And so he will be talking about the role of the smart grid in facilitating the integration of renewables. So let's welcome Professor Sayfur Rahman. And so let me first maybe to say a few words about our famous guest. So Professor Rahman actually was IEEE president. This is a very known position in IEEE, and also he's currently IEEE president-elect candidate for 2021. So we all hope that he will win this excellent position for serving all around the world. So for all the power engineers and electrical engineers and many, many other engineers, and making our world better. So, okay, that's more or less it what I wanted to say. And please, Professor Rahman, give us your speech.
Thank you, Dennis. Thank you, everybody in Irkutsk. It was evening time, Moscow, St. Petersburg afternoon, for me it's morning in Washington, D.C. So as you see, the title, Role of the Smart Grid in Facilitating the Integration of Renewables. Two key things, smart grid and renewables. I'll try to match the two and show you how smart grid will be able to help bringing more renewables into the grid. So that's the objective. So what is a smart grid? Smart grid is a concept with many elements where monitoring and control of each element in the chain of generation, transmission, distribution, and end use allow electricity delivery and use to be more efficient. So this is the thing. We start in the generation station, transmission, distribution, all the way to your home or building or office. Smart grid goes all the way, not just the grid, meaning not just the transmission line, which is the grid, many other things. So that's the thing. We want to make it more efficient and safer. Look at this. This is the electric power grid. Grid means network. It's a power network, high voltage lines. Russia has many. US, China, most countries, larger countries have long distance, high voltage transmission lines. The transmission grid today is quite smart already. It has PMU devices, fax devices to monitor its status, all the way to the substation. So the focus is not the power network as much, not the transmission network, but what comes below that, which is your substation, distribution network, and the like. So this is where I look at this statement. Why should we do smart grid? Because we want to make the grid smarter, safer, reliable, and more cost-effective. The key word, cost-effective, using advanced sensors, communication technologies, and distributed computing. It's very important. We will compute locally some activities and take local decisions. For example, if you look at large-scale solar photovoltaic deployment, sometimes the PV on a building rooftop or a house is producing more power than the house or building can use at the time. Excess power is then sent back to the grid through the network, and that's where you got to do some computing, making sure that the voltage profile is not going over the limit because of PV power coming to the network. So the keyword I'm putting here, I'm putting red letters, cost effective. You notice I did not say cheap. Smart grid is very expensive, it's not cheap, but it is cost effective. Why? If you look at this picture, I use this to explain the difference between a normal grid and a smart grid. On the left-hand side, I have the typical old black telephone, which has been around for more than 100 years. Cost in the US about $15. This is the cost of the black phone. On the right-hand side is an iPhone. iPhone 11 costs over $1,000. Phone is a phone. You make a phone call. So why should you spend, instead of $15, $1,000? This is the issue of value, not cost, because the smartphone gives you not only phone, it gives you, you can check Facebook, you can take pictures, you can do calculations, you can do your email, you can do WhatsApp, Telegram, all these things, because it is giving you the mobile phone, the smart mobile phone, gives you more choices, more features, you spend the money. That's exactly what's happening in a smart grid. Smart grid, smart meter, smart network, telecommunications, and so on, gives you much more opportunity to control the network than you could do with your old grid. This is the difference. So how does it work? Well, look at this picture. What are the starting and ending points of the smart grid? Obviously, the grid starts at the power station where energy is produced, then carried over to the load center using high voltage transmission lines. Once it reaches the load center substation, there you start the distribution network, which will carry that electricity from the substation to your building, your home, and your equipment inside the house. So you have the power plant, transmission line, distribution network, buildings, homes, businesses, and end-use appliances. So I'd say, when I give this talk, the smart grid starts at the generator, ends at the refrigerator. That's the difference. The grid that you saw, the high voltage line, this grid is only between the power station and the substation, nothing more than that. But then your smart grid goes all the way to your air conditioner, your water heater, your appliances, everything else. So that's the grid extent. Okay, now, what are the building blocks of the smart grid? At the top, I have technology, which exists today. A smart meter, fax devices, control technologies, all of that exists today. Most of the world, that's done. Next is standards. We know the smart grid technologies are manufactured by many, many companies. For example, smart meter done by at least 5-6 companies that I know. We have to make sure that as we deploy technologies from multiple vendors, they follow the same standards, so they're interoperable, meaning part of the network may have Siemens meter, another part of the same network may have network from Switzerland, GE, all of that. So how you make sure that multiple manufacturers, multiple vendors are marketing technologies which are interoperable, otherwise you're stuck. That work has been going on for at least 6-7 years now. And we pretty much have good standards for smart grid components. Next is rates and regulations. Smart grid only makes sense if you are able to use electricity at different rates, kilowatt rates, because prices are changing. If the price of electricity is same 24 hours a day, then you have no incentive to store the energy and use it during peak hours because money is the same. If, for example, the cost of electricity is 3 times as much in the afternoon on a summer day compared to the night before, then you have incentive to store the energy, electricity in a battery the night before and use it during peak hours on a hot summer afternoon. That's why rates and regulations are important to make the smart grid functional. Finally, at the bottom of this pyramid, I have consumer awareness and education. Very, very important. That has not been done yet fully. If the customer, you and me, do not understand the benefit of smart meter, smart grid, we don't care. We don't take any action. Because smart grid is not cheap. In Virginia, where I live, the average number is to put a smart meter in a house or a building costs the power company more than $200 each. It's not the meter cost alone. The meter, telecommunication, to read the meter in real time, store the data, all of that put together costs more money. So why should you and me spend more money to put a power meter in my house if I don't know the value and the benefit? That part is still being worked on. And I, as an educator, take this very seriously to make sure my students, my colleagues, my family understand the value of smart grids. These are the 4 building blocks we have to be aware of, and we can work on any of these 4 options to give our contribution. Okay, now, what has changed over time? How the grid has evolved? Well, if you look at the upper half of the screen, I call it before smart grid. Before smart grid, power was one-way flow, meaning it starts at the generator, goes to a step-up transformer, then it goes to the high voltage transmission line, power comes close to your load center, voltage is dropped down to a lower number, then goes to local neighborhood, your street, your building, your company, all of that. That's the standard practice going on for more than 100 years now. The lower half of this picture has other things like solar panel, battery, electric vehicle, wind turbines. Those are new things. In order to make sure we can keep track of how much power being produced by the solar panel, how much energy being stored by the battery, how much power the electric car is using at the point in time, how much power is being produced by the wind turbine, all of that set of data has to be available to the controller. For that to happen, we must have fully reliable, high capacity telecom network so get the data in and out. That's the blue dotted line on the lower half of this picture. So that's the difference. Before smart grid, it was just power flow, power station to your home. Now, power flow can happen in multiple directions. If I have rooftop PV in my house, I have excess power, I sell power to the company, power company, not buy from them. That's the difference. Anyway, so we have to have a reliable power system to begin with, and then communication system to make it work. Okay, now this is a good example of the components of a smart grid. Many of you know microgrids, which are smaller sections of the grid. You see, I got 1, 2, 3, 4 microgrids here. We have multiple homes, network, electric vehicle on the top in the middle section. On the top right, I have another microgrid. In the middle, I've got a bigger microgrid. At the bottom, another microgrid. You see, every microgrid has a base station, an antenna. That means they must be able to communicate in real time. So that's the setup of a microgrid, which will give me options to control locally. That we said before, distributed computing. If you focus on the picture on the top, got a 4 homes, 1 double-story home and 3 single-story home. They are a microgrid. If and when they lose power from the main grid, they can still function because they have enough storage, maybe rooftop solar, maybe some small gas turbine to keep them going. So that's what I mean by component of the network, which is a microgrid, can function without the network available all the time. Again, as I said before, my focus is reliability first. So this is how I can provide more reliability. Line can fail, transmission line can fail, but you can locally manage it quite well. That's the definition. Now, how do I make it work? Here in a smart grid, I merge power flow with information flow. That means I have communications going both ways. Here's the picture. This is your typical electric power infrastructure. Just power part, not communication part, power infrastructure. Power station on the left, upper left, long distance transmission lines, substations, network distribution system, low voltage substation in the middle. Then on the left-hand side at the bottom, you got homes, you got factories, you got offices. All these are fed from the power station. One-way traffic, fine. Now, to make the grid smart, I am introducing an information infrastructure on the power infrastructure. You notice information infrastructure has these red arrows. They go both ways, up and down. That means it has to provide two-way communication to make the system work. That's the new thing. Two-way communication, telecommunication, to keep the system status known to the system controller. Okay. So, but now the life is changing. It is no longer a coal-fired or nuclear power station serving the network and the community. You have wind turbines, you have rooftop solar, electric vehicles. All these components have to be taken care of and managed. That's why microgrid and smart grid comes into play. Okay. So we have now distributed generation. What are the characteristics, issues? Wind and solar are intermittent. There's no guarantee you'll have wind power an hour from now. Number one. Number two, talk about hydro. Russia has a lot of hydro. Hydro power is not intermittent because you are usually using a flow of the river, or you have stored water on the upper reservoir. But you cannot build a hydro plant everywhere. You can put a rooftop solar on a building in Moscow, but you cannot put hydro in downtown Moscow. That's the difference. Therefore, the resource is free. The wind and the sun and the water from the rain is free, but it is not always usable. For example, I'll show you later on, sometimes wind power is strong at night, demand is low. That's an example. It's free but not useful because you're not able to use it with the load being so low. You can store it, but that's a different story. Okay, now let's start with wind power first. Wind energy is both onshore, offshore. We'll talk about examples in the US now. I'm going to show you the actual load data from a power company. BPA stands for Bonneville Power Administration in northwestern part of the United States. In January, winter time, the blue line shows you the peak load. The load peak load, it has two peaks, typically what it is in the US. Two peaks in winter and one peak in summer. However, the wind output average for a month of January is the red line. It is moving. It is fairly halfway during the morning peak. Then it peaks in the afternoon when the system peak is low. And then second peak happens about 6, 7 p.m. The wind power is low. That means there's not a good match in the winter season for northwestern US between wind and demand curve. Number one. Let's look at April, springtime. Again, you got two peaks. The wind power is very different. It's high at night time in spring, is a typical number, and slowly goes down and goes to almost 20%, 10% in the early evening till about midnight. There's not a good match between the two. Keeping in mind, we have to accept the fact wind we cannot change. What can we then do to make sure wind output is more useful to us going forward? That was springtime. Now summer, July. July in the US, summertime has single peak, typical number. You can see the very wide single peak for the whole day from about 11 a.m. till 7, 8 p.m. Then you look at the red lines, which is the wind power output, is lowest in the evening when the peak was highest. Again, not a good match. Last one is autumn or fall season, October timeframe. Again, I got back the 2 peaks, but then again, you see the second peak happening about 7, 8 p.m., the wind power is low. This is my challenge. Power is not there when I need it, and vice versa. What should I do? Keep that in mind. That was wind. Look at this as well. This is the short-term variation. Data from a wind farm in Texas, 150 megawatt capacity. Suddenly, about 5 a.m., the wind output drops by 43 megawatt in 1 minute. So it goes to 70% or 60% capacity in 1 minute. That is not a good thing for the supplier. That's one. Next example is this one, even bigger drop on a different day in same 150 megawatt wind farm in Texas. Again, in one case, about 5 in the morning, the 150 megawatt system dropped by 113 megawatts in 10 minutes. So how do you manage your load if that happens? Those are the challenges we got to deal with. Then after a couple of hours, the load shoots up by 106 megawatt in 10 minutes and then stabilizes. That's the standard practice. That's wind. Longer term wind, again for Texas data 2008 in January. January 1st is about a 4,500 megawatt wind farm. 2,000, maybe 2,200 capacity at midnight. Slowly drops to almost 50 during daytime and picks up. J1, January 1st. Day 2, January 2nd, it stays low below 500 out of 4,500 for most of the day. By about 4 o'clock, 5 o'clock, starts to pick up. That's 2 days. Look at next 2 days. Same wind farm in Texas. So January 2nd was low, 1st was lower. 3rd of January is very good. It is running at close to 3,000 megawatt most of the day. This is my challenge. You can say when this happened, I can buy batteries and put the battery to store the energy at night, and daytime when the battery is fully charged, demand is high, wind is low, I discharge the battery. You can do that. But then when this happens, you don't need the battery anymore. That means the battery is not fully utilized every day. And that's an issue of investment and return. So number one, battery is very expensive, but if you cannot use it every day, it is not going to be cost effective for you. This is the challenge for batteries. Okay, now let's look at solar. This is my building at Virginia Tech near Washington, DC. We put rooftop solar to see how the building load and the solar load match or do not match. This is rooftop. So I'm showing you some data from this system for a few months. Now, first of all, this is summertime, no problem. Then winter time, problem. Nobody will go to the roof to clear the snow. If it snows, we leave it there, and our output goes to very small amount in the snow, then we live with it. Then the question is, if this is your only source of power in the building, you'll be in bad shape. So what do we do? We'll talk about that. Let's see some data from the same system over a week. See, this is a very, very good week. I am showing 7 days solar PV photovoltaic output. It's pretty good every day, sunny, fine. Now I look at this another week, same system. Monday was low, Tuesday, okay, Wednesday, good, then drops again. So my point is, this is life. It happens this way, happens this way. How you deal with it, number one. Number two, let's look at a daily variation, not the weekly variation. This is a good sunny day here, but even though it is a good sunny day, I'm getting rated power at midday, 1 o'clock or so, have been a lot of variations during that same day because of cloud movement. So what do you do when the cloud comes in for a few minutes, output drops by 50%, and then goes back up again? So I'll show you some examples how we can deal with that situation. Again, this is another day, daily output, highly variable, and we have to deal with it. These are the challenges. Now, these are solution options. We have battery, talked about this. We have pump storage energy. we have compressed air energy storage as well. Battery, we know all very well, fine. Battery is expensive. It is typically used for shorter term variations. Pump storage, on the other hand, can be used over a weekly cycle. You fill it in over the weekend, use it during daytime, fill some more at night, use the same stored order the next day. It's going on for a long time, but you cannot put a pump storage plant everywhere. Battery you can, pump storage you cannot, number one. Second is example here, compressed air storage, which is an example of where you will get the air from the atmosphere, from the ground, compress it using a pump, and then push that compressed air into a salt mine or some reservoir underground, hold it there. When the demand is high, you release that compressed air to a gas turbine and make the turbine run more efficiently. Again, that can be located only where you have storage capacity, otherwise not. So that's a set of examples we can deal with. These are solutions. Now, I have other solutions also. That was a supply, this set I call supply side solution. This is demand side solution. We have talked about many demand side solutions in the literature. I'm talking about only two. One is demand response, which is a customer action to control their load to meet a certain target. For example, hot summer afternoon, power company, in my case does, send a signal to me that they would like me to drop my peak load by 20%. If it was 20 kilowatt at the time, I can use 16 kilowatts, not 20. So they can save the 4 kilowatt from my house and use it to help somebody else. Here, the customer chooses what load to control and for how long. Meaning I have air conditioner, electric water heater, I have oven, I have clothes dryer, I have electric vehicle. All these are higher voltage system in the US, 240 volt. So those I can decide how much to control. Maybe I will not charge the electric car at the time, which is a 5 kilowatt load. I will cook rather. So that's the customer choice. That's demand response. Other thing, which is a much older solution called demand side management. In that case, the power company controls my load if I give them permission. So they will choose only my air conditioner, not my electric water heater, electric vehicle, or clothes dryer, only air conditioner. So this happens today in the US. On a hot summer day, if the customer has allowed the utility to control their air conditioner, power company will control them, meaning turn them off. It's hot outside, AC turned off, not very comfortable. So I prefer demand response, not demand side management, but demand response needs more technology. We'll talk about that. So here you go. This is the new paradigm for the power system today. Historically, it has been demand-driven supply, meaning we forecast the demand, and based on the forecast, we build power stations. That's going on for over 100 years now. The new reality with the rooftop solar, with the wind turbine, with the battery storage, I call it supply-driven demand. That means not my demand, my supply is fluctuating. So how do I manage so that supply fluctuates? So demand has to fluctuate to match. This is what I mean by demand response. You saw those lines on a sunny day. Solar is good, but it fluctuates a few minutes. If when the solar output goes down on my rooftop, if I could reduce my demand in the same amount by raising the temperature set point on my air conditioner, dimming some lights, turning off some ventilation fans, I could manage with our storage. That's what we call supply-driven demand, which can adjust to meet the fluctuating supply with some storage or demand control. That is what I call smart grid ecosystem. And that's the ecosystem I'm talking about. Ecosystem at the bottom has smart building. I just said I can manage my load by changing the thermostat setting for the air conditioner. I can dim my lights. I can turn off some plug load like electric water heater. No, I don't have to make a tea at the same moment. Or I can turn off some large ventilation fans in the building for a few minutes. Nothing would be problematic. Can be done. That's smart building. Now I go from smart building to smart campus. A campus, a university campus, has multiple buildings. Each building can do something to help out. From smart campus, I go to smart city, which has multiple smart campuses, many buildings, shopping centers, and the like. So if I can get the same concept I just talked about, temperature control for thermostat, ventilation fan, smart plug, smart load, all that can be done citywide. Then you got multiple cities in the smart grid network, and if all of them are contributing, then the network can respond during the low output time for wind and solar and control the load such that the demand is met without any interruptions. Next one. What makes a building smart? It's a single platform, very important keyword, single platform to monitor and control heating, ventilation, air conditioning, lighting, water supply, using sensor networks and security camera and fire emergency. That picture is there. I have sent Denise a copy of my slide presentation, and please free to distribute that or put on your chapter website, no problem. So people can see this going forward. Okay. Now, there was one building. If I have a campus situation, I have a large number of buildings which can be controlled selectively to absorb these fluctuations of power from, let's say, solar rooftop system. If I do that carefully, I don't need to put storage battery in every building. I can battery in some buildings, but I take advantage of my flexibility in demand to reduce the need for storage. That's why I say minimal storage is required. The main investment you are doing for this case is not the battery, but for putting sensors in the building to monitor the temperature, humidity, noise, all of that, and control them. This is the difference. So some battery, yes, a lot of batteries, but focusing on demand side control. So this is how I plan to address intermittency in renewable generation. We can do two ways of load control, smart and not so smart. What is a smart load control? You don't turn anything off. You change their level of intensity. And not so smart control is turn the power off, like it is done in the US for demand side management. They will turn the air conditioner off on a hot summer day for about an hour or so. That to me is not very smart. So I would adjust temperature setting rather than turn the AC off. Similarly, I would not use brute force to put storage capacity in every building, high amount, it's expensive. So I would size my storage unit based on how much I cannot manage using demand dynamics. If I can manage using demand dynamics, all of it, I don't need storage. So now you have the renewable generation, solar, let's say, is changing. If I could adjust my load simultaneously using a smart inverter, I could manage the building. So that's what I am talking about. So this is my last slide. As Dennis said, I'm running for the IEEE president this year, 2020 election in August. I have been PES president. I was part of the IEEE board some years ago. I am very proud of my accomplishments in PES. I established the PES University. If you go to PES website today, you'll see the university page. I have also established a corporate engagement program where the power company pays the IEEE dues for the member, not the member themselves, and in return, the company gets benefit from IEEE. And then, of course, I've set up chapters councils where chapters get together and do some program themselves. I've done in India, China, Africa, Latin America. Again, this is my website for my election, srahman.org. I'm also Facebook, LinkedIn, Twitter, and YouTube. So I'll stop here, Dennis, and maybe we can now take questions. Thank you very much for your attention.
Thank you very much, Professor Rahman, for the...
Thank you.
So now we have time for questions, and I also ask to type the questions here, and also you can do this, I think, by your voice. I believe we can do
unmute themselves. Yeah, unmute.
Okay, I have some questions from Professor Popov. Yes.
Okay.
Your question. Okay. So you can speak, I think, now.
Denise, I have one question.
Yes, please.
Okay.
Hi.
Yeah. Hi. My questions. First of all, thank you for your interesting presentation. It's really very interesting. And my questions about autonomous intelligent control. What do you think about prospect of development and implementations? I mean, fully autonomous control system in power system. I mean, to similar, for example, state of art autopilot in self-driving cars. It's similar to this technology, because now we have some technologies, for example, deep reinforcement learning and deep learning, which can reach superhuman performance, and, for example, in power system control. For example, in our institute, we have one project. This title of this project, Artificial Power System Operator, because we have idea to join automatic control, for example, automatic emergency control and operative control with people, operators, and so on. What do you think about my questions? Prospect of development full autonomous intelligent control systems for power grid, for smart grid?
Very good question. Very good. Excellent. My response is, I have given you some concepts here, like building load management, air conditioner control, smart control of ventilation, all that. That we do using some machine learning. For example, I have to know when can I turn the ventilation off? And if I keep it off too long, it'll cause some health issues. Those are all taken into account. That question is answered in two ways. Not only what the health issue, how many people in the building. Not many people in the building, we don't need to control ventilation so much. That's an example. Then the question is how hot it is outside. Because outside is pleasant, 18 degrees, 20 degrees, you don't need to cool as much. So all that information has to be massaged in one big box. Outside temperature, occupancy level, time of day, the fan capacity, the power usage from the fan, all that. So all that gives you an AI atmosphere where many things have to be considered to come to a decision. You're right, this is not done. This could be PhD thesis, or many PhD theses to answer these questions.
Yeah, okay, thank you. Thank you.
Thank you, Nikita, for...
Thank you so much.
Any other questions, please? Please feel free to come up like Nikita done and ask question. I think Sergey Popov have some question before.
Just to add to Nikita's comments.
Okay, sorry.
Yeah.
Please go ahead.
Okay, yeah, please go ahead. Yes, Sergey.
Sergey? Or...
He raised his hand. So
there's a question in the question here.
Okay, there is a question here, yes.
I can read that question. Okay. The question is, what are your views on the price of electricity considering smart grid implementation, especially huge share in distributed energy sources and high cost of battery storage stations? Very good set of questions. As I said, smart grid is not cheap, it's expensive. But for example, today in Virginia, now, solar power cheaper than coal power today, cheaper than coal, at the same price as natural gas. So if I use coal, I have to charge my customer more money because my cost of production is high. If I use photovoltaics, not only issue of environment, put that aside for a minute, I'm producing power at a lower cost. I'm saving some money. So that's the issue I talk about. The money I save by using solar power compared to coal can be used to pay for all the stuff I talked about. Number one. Number two, it gives you better control. For example, I can make a building more health conscious by managing temperature, ventilation more carefully, part by part in every floor of the building than whole building under one control system. That's why it is important for us to do what I call distributed computing. The answer is yes. These are expensive things, battery storage, for example. But the point is the following. I showed you the data from northwestern US. Nighttime supply is high for wind, daytime supply is low. So if you're not using the nighttime wind supply because load is low, you are throwing away that wind power, throwing it away. If you put that in the battery, then the energy that you are putting in the battery can be used in the afternoon, which was otherwise coming from nuclear or coal or gas-fired power plant. So we have to do this in a big mixture of things. Individually, they are expensive, but if you look at the overall mix, it makes a lot of sense. So I hope that answers your question.
Okay, thank you very much. Evgeny, is it answer your question? Evgeny Abramchenko asked this question.
Another question here. Popov. Is the system boundary for smart grid versus power grid about kilowatt versus megawatt, or distribution versus transmission voltage up to 110 kV, or supply driven, demand driven? Is it all together just IT plus power grid? Very good questions. Okay, let me start from the bottom. Number one, for the grid to be smart, I must provide IT. This is infrastructure issue. One is infrastructure, one is function, two different things. So infrastructure is yes, you need IT and power grid, infrastructure. Now functions, what does smart grid do for you? It looks at the high voltage line, which I don't touch because this is determined by the power station supply level. I am focusing more on the demand side. So you're right, it's demand driven. How can I adjust my demand so that I am more in line with the supply side options, meaning more solar, less solar, more wind, less wind. So smart grid is the power grid, which has been modified by including IT and become smart grid. Same physical grid, modified with IT applications. That's the infrastructure. And the function is demand driven, not supply driven. I hope that helps. Thank you.
Thank you, Professor. And so I think Sergey Popov, he raised his hand. Please switch on your microphone and ask us the question if you haven't. I can see the raised hand, but he's keeping silence. Okay, I have some question.
Please.
Yes, and so now we can see there is a big, it's getting more popular, this energy internet things.
Correct.
What is your view on the future of energy internet and
okay.
In which direction this is
Very
going?
good question. Very good question. I have given lectures at a conference in China, Beijing, on energy internet. The conference is called Energy Internet Conference, IEEE conference. Yep. Now, the way I look at it, we all know what internet does. Internet is internet allowing people to buy and sell things, talk all over the world. To me, energy internet is the internet of energy. That means you saw the solar power in one power company, wind power in one power company. Ideally speaking, if we can do this with communication technologies all over the world, you can, Dennis, can buy power from South Africa or Saudi Arabia over the internet. Meaning, your system will be able to tell Saudi producing so much excess solar, and then Siberia has excess water, and you like a menu on your screen. And you can program it so that you can buy power from anywhere, anytime. But for that to happen, you have to have reliable network, of course, and that is not there yet. So, and number two, difference between Amazon selling me a book and Saudi Arabia selling a power is different. Book can wait 2 days to get to my house. Power can wait 2 days. It's here right now. So how do you build a network which is reliable, enough capacity to move power back and forth? So to me, that is the energy internet. That is how you make it happen. I have written papers on this topic. I have a grant from US government now on energy internet, how to make it happen. I can send you some information later on if you are interested, Denise.
Yeah. Thank you very much. Yeah, this